how they are being used, right? Because for us as users,
is being publicly streamed.
For us as users, we use them by calling APIs, right? That's for those of us that use them on a surface level, all right. And then some of us we get the model weights, like we get the model weights for open source models, all right, to serve them ourselves. So we are using them in different dimensions, but again, we still have to understand what constitutes the inner workings of these models. So I'll be taking us through that. And again, there's also this misconception that the idea of artificial intelligence um arose from the arose during the initial iteration of ChatGPT. I think that's the first ChatGPT that was made public, right? And that's like GPT-3 Turbo, if I can remember, or GPT. I think GPT-2, then GPT-3. All right. Some of us would have felt that is when we started having large language models. Or started having AI models. All right. But in fact, it is not so. All right. We've had over the years, we've had different iterations of language models, some of which we use in our phones, but we are not aware that these are AI models. All right. So it doesn't have to be too magical for it to be AI. I think at this point, some misconceptions we have about how these models work, we're already discarding them, right? And so we'll be discarding more of them, and not to take away the flair from how we use these models, but I mean, if you understand the inner workings, it will enable you to use them better. All right, you're using them from not just an appreciation point of view, you're using it from a technical point of view. So, understanding LLM architectures. My name is Daniel Akhabue. I'm an ML engineer. And as of this afternoon, I've definitely been considering farming. My models have been, my models have been taking me through certain depths of horror, right? So, deeply considering farming. But before I quickly make that career change, I would share my screen. I would share my tab so that I would walk us through today's class. So let me do that quickly. Okay. Okay. Um Give me a minute. Let me set this up. Yes. I think this is okay. All right. So let's have this then. So we are dealing with what I would call, by the way, if you have any question, please feel free to drop it in the chat. So we are dealing with LLM architectures. All right. Already we like I stated earlier, we know what LLMs are. We know that they are large language models. All right. They are large language models. And they are AI models that generate text. All right, it's not just generate text. They do text summarizations. Some LLMs do text translations. All right, so you could ask a question in Yoruba, for example, and get the resulting translation in French. All right, some LLMs have these capabilities. All right, so we are well versed with how LLMs work. All right, we know how to use them. While on the surface level, I mean on the application layer level, we know how to use them on the development level. All right, some of us even know how to use them on physical level. I mean, dealing with the raw weights themselves, right? Dealing with GPUs, all right? Serving these models raw from scratch. We also have understanding of that, right? And if we do not, we would get there one day. All right. So it's important to also point out that what we call ChatGPT, cloud models, Gemini models are all belong to the family of GPTs, all right? What we call generative pre-trained transformers. Right? Generative pre-trained from transformers. They all belong to the same family in essence. All right. And then it's also important to mention that because they belong to the same transformer, they share similar architecture. And this architecture is called the transformer architecture. So I want us to follow me clearly, because I'll be taking us some steps backwards in time and bring us forward so that we understand the progression of how these models have evolved over time. So your Claude, your Gemini, your GPT models, that's OpenAI GPT models, mention it, your Mistral, your DeepSeek, right? They share the same family of architecture, right? And it's called the transformer architecture. Yes, some things might differ, which of course contributes to why they are different in performance, difference in in speed and other features, but they still at the core of these models, they share the same architecture, and we call it the transformer architecture. So when we say LLM architecture, what we are trying to explain is the transformer architecture, because this is what powers the LLMs in the first place. So we'll be talking about the transformer architecture. Now, before we go into transformer architecture, I think it's also pertinent to explain that LLMs are not the first language models. All right. Before now, we've had models like RNNs, all right, which we call recurrent neural networks. All right. We've had LSTMs, which we've called long short term memory. All right. So we've had various variations, all right, of language models even before we had LLMs. Right. It's just that some people on I think the large scale adoption of language models or AI models started with transformer based models like GPT models. All right. But I would it will interest you to know that before ChatGPT came, right, came around, we've been interacting with these models. For example, how many of us have always used you've been chatting, so on your keyboard on WhatsApp, for example, and then you're trying to type something, and then as you type the first word, you are getting suggestions for the next word. All right. So, and you're more like, how does this keyboard know what I'm about to type next? We've been using that technology even before ChatGPT came out. All right. We've been using our keyboards, right? In some of us even call it auto complete, right? Once you type one word, it gives you the next three words, next four words, next five words. Those were previous adoption of language models even before the transformer based models like GPTs. All right. So and RNNs and LSTMs constituted those kind of models. All right. So the idea with RNN, which I'll go later on when I'm trying to compare with LLM technology, is that all right, for RNN, all right, is that we're doing sequence to sequence generation. So for RNNs, we are generating one word at a time. All right, one word at a time. Funny enough, the architecture of RNNs are not really far from the base deep learning architectures that we're already learning currently, right, in our previous classes. All right, where you still have your sorry about that. So when you still have your inputs, so you have your inputs, all right, then you have series of layers, which you call our hidden layers, all right, and then we have our outputs or output layer, all right. So let's call this input layer. All right. So the architecture of RNN is not so far from our basic neural network architectures, right? So not just the way we doing using deep learning for doing regression modeling. I think the ML guys would understand that better because we took that in class. Just the way we use neural networks to do regression, at least to predict a word, I said the word, a value, right? The same way too for RNN, you are predicting the next word. So which means that in predicting a word, you are going to have your hidden layers changed. All right. So as you perform a particular operation within your neural network, you'll be adjusting for your hidden layers. All right, using back propagation and all that. So which means that as you keep predicting for more words in your hidden layers, you're adjusting various parameters. Now, the problem with RNNs was that as you keep evolving the hidden layers, for example, I'm doing something like my name is Daniel. So Daniel is an AI engineer. All right. So as you keep predicting for the next word like that, the hidden layers keep changing. All right. They keep changing. And the problem with this is that as it keeps changing, it will keep losing information. It will keep losing information. So what I mean by information, I mean context. So by the time it has gotten to AI, all right, it has lost certain information backwards. So it might have lost information relating to Daniel. So the problem with RNNs at this point was that it was difficult to keep context for a long time. So that's why they were not so perfect, which is the reason why they were only used for they were only used for applications that require just brief words generation. For example, like your text completion or your autocomplete in your keyboards. You are just predicting for at least 2 words, the next 2 words or the next 3 words. Or maybe you are in your Gmail and you are typing the first word and it's giving you at least the next 3 to 4 words. All right. But it could not give you an entire sentence. But the current iteration of language models right now can give you a full sentence just by 2 words or 3 words or 4 words, right? Depending on how you prompt it well. Okay, so this was the I would call it the shortfall of RNNs, recurrent neural networks, right? Sequence to sequence. It was difficult keeping context because the hidden states, all right, kept changing. Now, for every operation that is, performed in the neural network, there is state that has to be changed, all right, due to adjustments, all right, from calculating your loss function and things like that, all right. So the states will keep changing. Now, with more hidden states, there'll be more changes to context. Now, that was a shortfall of RNNs. Now, LSTMs now came. LSTMs is long short-term memory. From the word long short-term memory, it wasn't perfect, but it tried to solve the problem that RNNs used to have, right? Which was the issue of keeping context or keeping memory. So it performed that with what I would call gating mechanism. All right, gating mechanism. Now, the idea of gating mechanism, to be crude, it's more like it's like it's gating something from what it's gating something. And the idea of gating something means it's protecting something. So with the idea of gating mechanism, LSTMs are able to choose which information to discard as you are changing your hidden state. Like I said, your hidden state is somewhere here. So this could be hidden state 0, hidden state 1, hidden state 2, hidden state 3, right? It's just parameters that are changing over time. Okay, so the idea of a gating mechanism in LSTM was a way to choose which information to discard from the future. From the past, which information to discard in the present, so that at least you don't just accumulate so much noise. You're able to choose specifically what is needed for the next, text generation. So that was what came about LSTMs. Then over time, we had started having more development in the area of artificial intelligence, maybe not just language models, all right, or LM or NLP. We started having GANs, right? And then we started having what would you call it now? More advancements in AI, right? See, we got to transformers. So with show of hands, all right, how many of us have studied the research paper Attention is All You Need? Okay, David, Solomon, just David and Solomon. It's just David and Solomon. Okay, so if you've not read, let me note that down. Okay. Attention is all you need. All right. Please, if you've not read this research paper, maybe after this class, I think it would be more interesting to read. But please, I would want you to read. I don't think there's any serious AI engineer out there that you claim you're an AI engineer or AI developer, whatever appellation you want to go by, and you've not at least studied that paper, because that's just the foundations of the transformer architecture. Or that's research paper that's brought about the transformer architecture that every other company, every other startup, every other big organization they are adopting, right? So at least if you want to understand what is happening a bit, because I'll still I'll talk a bit in the paper, I'll talk a bit about some things that we're discussing that paper on the call. So but I want you to read it. All right, just go online and type Attention is All You Need paper. You see it. And please study it. Some things might be gibberish, yes, but with today's class, you would have an understanding of some things, so it will not be difficult. Okay, so now we've dealt with a bit of the past, and let's come to the present, and we'll be talking about LLMs, specifically transformer architecture. I've already established that when we talk about LLM architecture, all LLMs belong to the same family, all right, and they have the same, their family has share the same architecture, all right, and which is the transformer architecture. All right, transformer architecture. Now, even within transformer architecture, we have subfamilies. We have encoder only. All right. We have decoder only. And then we have encoder decoder. All right. So I will talk about these families, these subfamilies, but specifically I would emphasize on decoder only architecture. All right, because the LLMs we use right now are actually built on decoder only architecture. Okay, and I would explain why on the call. So before I go into the technicalities of these subfamilies, I want to just draw a brief architectural a brief data flow of how LLMs work. Now, let's take a word. Let me choose someone. Let's say Damilare. So let's say Dami. All right. Now, Dami is a word. Just like the way you type in your ChatGPT, you don't type in numbers, you type in words. Now, from our machine learning background, we know that these models are algorithms that have been modeled after data. So it's beneath it is still set of equations that still perform this analysis, predictions, classifications, name it. So it means that if you say an LLM is a model, what that means is that it still work on the same principle of our machine learning models like linear regression, cat boosts, algorithms, light gradients, boosting machines algorithms, right? So it means that it can't handle text. it needs to work with numbers. So when you type in dummy to your ChatGPT or your Claude or your Gemini, something goes beneath that you do not know. Now, when you type dummy, what happens is that dummy is tokenized, all right, and we call this tokenization. Now, what happens in tokenization is that dummy is converted to what I'll call a numerical representation. Now, this numerical representation is like an ID. So it is to just say, okay, ID 909. All right. That is the numerical representation for dummy. Now, after we've tokenized dummy. So by the way, it means that every word you type into ChatGPT is tokenized. Every word you chat into ChatGPT has a unique ID attached to it. Wherever you use ChatGPT, whenever you use ChatGPT. Now, after it has been tokenized, all right, of course, you do not see this tokenization. The next thing that is done is what you call embedding or vector embedding. Now, there's a reason why it is tokenized, is that we are mapping vector embeddings to that ID. Now, vector embedding is just it's an high-dimensional representation of that word. All right, it's an high-dimensional representation of that word. What I'm trying to say is that it's just like a list of numbers. All right, 3, 4, 5, 6. I'm not saying it flows like this, but an example. So this is a vector representation of the word dummy, which means that anywhere you see dummy, this is a vector representation of the word dummy. All right. And to do these vector embeddings, you need what we would call an embedding model. Now, every large language model has a differ. So since they are different, every large language model differ by several things. Now, a key part of their differences is the kind of embedding model that is used to embed the vector, or to like embed the word into vector representation. So which means that OpenAI is using a different embedding model from Claude, and Claude is using a different embedding model from Gemini. All right. And every vector embedding has, I'll call it a dimension. All right. So now, for those of us that might have watched the ML class when we talked about neural network, we talked about input dimensions and how the dimensions contribute to what goes on within your hidden layer. All right. We've said that the more dimensions you have, the more computation, the more complexities, the more understanding is going on within your neural network. So the higher the dimension, the higher the number of, it's like number of variables, like, the number of processes that would, will be done within your neural network. The same goes here, right? Now, based on the kind of embedding model you are using, it also contribute to the dimension of your vector representation. For example, OpenAI might say that the dimension of the vector representation for dummy or their words, right, should be 109, right? 109. Which means that in this list, you would have 109 values. Claude might say, oh, I want the number of numbers in my vector representation should be 205. All right. This can be for OpenAI, for example, then this can be for Claude. All right. So this is the reason why each of these models differ a lot. So these are one of the decisions that are being taken that contribute to why you use a GPT-4 model, and the GPT-4 model will be largely different from your Claude Opus or a Sonnet. Decisions like this. Now, I also explained in that class that you have to be careful with the number of dimensions you indicate. All right, because the more dimensions you have, I mean, the more you scale your dimension, the more you should scale your data. So scaling your dimensions or number of vector representation should be directly proportional to the size of your data. So if you have a very large dimension and your data is small, your training data is small, you'll be running into a lot of overfitting problems. The model is actually not even learning anything. All right. So that is why larger models, very large models, have higher dimensions, which means they also have the higher capacities to learn more textual representation, things like semantics, things like semantics, word capturing, grammatical representations. So that's why the bigger the model, the better the model. I mean, according to scaling law. All right. So that is why the bigger the models too, the longer it takes them to train, because the number of input dimensions are bigger, they are larger. So it has to go through all this before it comes out with a particular output. All right. So now, not to dwell much on that, we understand how vector embeddings work. Now, the next thing is what we call positional embedding. Now, positional embedding will take me to something I would have to quickly describe. So, when we talk about LLMs, or maybe we've seen it online, all right, we've seen it in books, we've read it in articles, and you hear that LLMs work on what you call self-attention mechanism. LLMs work on what you call self-attention mechanism. Now, the reason why it is called self-attention mechanism is because of how it is trained. Now, let me explain that briefly before we go to positional, because we need to explain this to get to understand why we need to do positional embedding. All right. Now, back to my example of Daniel is an AI engineer. Now, what self-attention means is that to predict the word is, all right, every word before is, in fact, before I even get to self-attention mechanism, scratch that. I need to also describe what we call next token prediction. So just in case you see these fancy words online, you already have an idea of what is happening. So next token prediction. Please, if you have any question, drop it on the chat. Next token prediction. Now, what next token prediction does is that these models work by predicting the next word. I did explain what next token is, the next ID, and these IDs are mapped to the words. So we could as well say next word prediction, which means that Daniel is a boy. These models work such that before a boy is predicted, is has to be predicted. And then A is predicted, then boy is predicted. But it works very fast, of course, with high computation. So you don't exactly see the time taken to generate one word at a time. Okay. So each word is predicted before the other. So when we say, oh, LLMs work on next token prediction, or you hear things like, oh, LLM models, or LLMs rather, are auto-regressive models. What that says is that each token is predicted one at a time, or each token is predicted before the next token prediction, or auto-regressive prediction, from the word regression and all that. It just predicts next word one at a time. Okay, so now that we understand what next token prediction is, then I can now boldly talk about the self-attention. Okay, self-attention. But to do that, let me quickly switch to this. So next token. All right, and then self-attention. Now, this is what self-attention is. Daniel is a boy. What this means is that if I'm predicting for the word A, don't forget his next token, left to right. I'll also explain a situation where this left to right doesn't really occur, right? Left to right is what we call unidirectional. There's something called bidirectional, and I'll explain what bidirectional is when I talk about the other subfamilies under the transformer architecture. But for now, let's stick with unit direction, because what I predicted from left, the English grammar is written or predicted from left to right. All right, so which means that to predict for the word A, Daniel has to contribute to what A is, or Daniel has to contribute to the prediction of A, is has to contribute to the prediction of A. Now, I would say the next sentences, but I'll explain later and contradict myself. But just follow me. For the case of the self-attention, follow me now. Boy would also help in the prediction of the word A. But I'll contradict myself later on, and I'll tell you why. Now, so unlike your RNN, where as you are going from left to right, the hidden states are changing. That's the hidden representation. What it has learned over time is changing. All right, so which means that by the time you are predicting for boy, you've actually lost the meaning of Daniel, has been lost in translation. Okay, now in the case of a transformer architecture, for every word in the sentence, okay, every other word contributes to its prediction. And that's the idea of self-attention. All right, self-attention. The prediction is okay. Yeah, we already know what self-attention is, by the way, from the word itself, self-attention. All right, so and now that we understand that every word contributes to the prediction of A, then we cannot go ahead to talk about what we now call masked self-attention. Again, just in case you see masked self-attention. Now, this will contradict what I've said earlier, and still using the same example of Daniel is a boy. Now, the idea of masked self-attention is that when I'm predicting for the word is, it doesn't take into account the contributions of A and boy. Now, don't forget that we are trying to build a model that is able to predict the next word from nothing. Not exactly from nothing, but it is not aware of what the next word is. So it's trying to learn how to predict the next word without having knowledge of the next word. That's the idea of why we want to build the word, why we want to have, a large language model that can, help with things like text generation, right? So which means that when you are training such model, you cannot infuse knowledge of the succeeding words in its generation. Now, if you do that, you are just adding, it's more like overfitting, right? You're just giving information about what it's supposed to predict to it. In most cases, it will not learn anything. It would overfit. Now, why is this crucial? This is crucial because you want a situation where it is not every time you see is that the next word should be A. So what I'm saying by this is that there's also a possibility that Daniel is outside. Again, he should not be aware of the word outside. In this case, outside is masked. during training for the word, is. So in this case, the model is trying to predict the word outside based on just Daniel and is. This is how we can trust the validity and the performance of a large language model. All right. Now, of course, it does still with the data set, the large data set is trained on rather. It will see various variations of Daniel is, Daniel is, Daniel is. All right. Based on based on how it's able to, based on what it has seen. I mean, after it has predicted the next word, of course, but at the very first time, it will predict nonsense. Now, by the time you now begin to calculate the error, you're able to readjust back. So I don't want to overshoot. I want to take us through the process one by one. But now we've established that this is called masked, which means that the word after a word that is being predicted for a word that wants, the word after, or the words after what is supposed to predict, right? The next word token prediction would be masked. So which means that if I want to predict for the next word here, all words after is will be masked. They will not be seen. I mean, during training, of course, they will not be seen because you want to try and let the model learn representations, not just see the answer. It needs to learn and understand what the answer should be. Okay, now that we now know self-attention and masked self-attention, all right, this will now bring me to how LLMs, right, how it handles the vector embeddings as established at this point. So now it will take me to positional embedding, which I was going to get back to. Now, because each word, again, using this example, each word contributes to, every part. I mean, if each word contributes to the prediction of a particular token, right, it means that each word, or in this case, each token needs to have a position. Now, the idea of a position is that because we'll be doing this same thing for every other word in the sentence, which means that, let me add more words. Daniel is a boy that attends Oxbridge, for example, right? The cleaning of this, it means that, and let's say clean of that as well. And we want to predict for, let's say, the word attend. Okay, the word attend. So this means that Daniel will contribute to attend. Is we contribute to attend. A we contribute to attend. Boy we contribute to attend. That we also contribute to attend. Of course, with the masked self-attention, at this point, the model does not even know that Oxbridge exists. So this does not exist at this point. Now, that attends. Each of these words themselves contributes to the word attends, which means that when we are predicting for the word boy, it is Daniel, is, and A that will contribute to the prediction of boy. Now, this means that this whole contribution, all right, like a jaw, as we do it like this, each token has to have what we call a positional embedding, so that at least the model understands where the words are starting from. It understands where each token is at every point in time. If it doesn't do it this way, we just have, a generation of one word, generation of another word, and all of them are just separate and they will mix up. So the idea of a positional embedding is that each word in that particular sequence or that particular sentence has a position. So even when you are using it to generate the next word or the next set of succeeding words, you are not losing touch on their position in that sentence. Don't forget, you are trying to train the model to predict accurately the next word in that sentence. So each word needs to have a position so that it at least know where each word stands. Now, that is why we need what you call a positional embedding. Now, in this positional embedding, you're already vector embedding, permit me to use the word VE, is added to your positional embedding, all right, it will now give you a final, we can just give final word embedding, all right? Final word embedding. Now, this is what would be used to now do your processing. So each word in Daniel is a boy that attends Oxbridge. Daniel would have something called word embedding 0. Of course, positional embedding. Is would have what you call word embedding 1. A is word embedding 2. That is word embedding 3. Okay, of course, attends word embedding 4. Oxbridge word embedding 5. All right. So now at this point, we have to now do transformation on, transformation on each of these embeddings. All right. And then that will now bring us to, I should be able to manage this space, okay, so that I will not lose context of some of the things I would be using. So that will now bring us to what I call Q, K, and V. Now, QKV are vectors that are computed from these word embeddings. They are computed from certain transformations, and each of them have certain meanings. All right. Now, like I like to call it, for the word, so which means that each for Daniel would have its own Q1, K1. By the way, these are vectors, right? V1. Is would have Q2, K2, V2. I'll stop at A. So A has Q3, K3, and V3. Now, Q, K, or these vectors have their importance, all right, in LLM training. Now, this is where we actually do the self-attention. Now, like I like to call it so I would understand it, from the word Q is called query, right? Query vector is basically, I call it what you are looking for, right? What am I looking for? What am I looking for? All right. K is called key vector. Like what we use, like the meaning of key. What do I represent? Those of us we know key value relationship in Python. All right. Your data structures, you know what key is. What do I represent? Then we have V. V is just the value vector. And what value vector is to me is what information do I contain? Do I contain? Now, this is computed for every vector embedding, again, or for every word in that sentence. QKV is computed for every vector embedding or every word in that sentence. Now, coming to QKV, I will establish that you are computing for both Q1, K1, V1, Q2, K2, V2. It means that when we now say self-attention, from the word Daniel, so if I'm predicting for, so Daniel is a boy. So which means that Daniel would have Q1, K1, V1. Is would have Q2, K2, V2. A is Q3, K3, V3. Then boy is Q4, K4, then V4. Now, Q1 is your query vector. What am I looking for? So which means that when we are doing self-attention, it means that at this point, Q1 for self-attention, if you are trying to predict for the word is, all right. Sorry, so if I just predict for the word is, it means that at this point, Sorry, please give me a minute. Pardon me. All right. So I apologize for that intermission. So now, like I was saying, we have Q1, K1, V1, Q2, K2, V2, and Q3, K3, V3, Q4, K4, V4. Now, at this point, what we want to calculate for is what we call attention score. So, like I said earlier, this is where the self-attention happens. All right. And we already have QKV vectors representing each of these words. All right. And we want to have, these QKV vectors are based off of the word embeddings, which is a mix, which is a combination of your original vector embeddings and your positional embeddings. But now this representation just represents the word itself. But now we want to have the representation of the word based off other words, which means that the representation for boy should be based on the meaning that it has gathered from Daniel, is, and A. Now, this is where the magic happens. And that's why we have LLMs working like we call them magicians. Some of us call it, I don't call him a magician. I don't call him magicians, by the way. But some people call it, it's the next voodoo. It's magic. It's the Antichrist. Many things you will hear. All right. This is where the magic happens. This is how, you are able to ask ChatGPT a particular question and to give you, is to generate something different almost every time. All right. If you ask it to give you and not give you like what is that generated for you in a different format, it will still give it to you. Because each word within the model has gotten what you call a contextual representation based off other words that it was trained with. So which means that the word boy in this case, the representation of the word boy is not just boy for itself. It's based off other words that it was trained with. In this case, Daniel is a boy. Don't forget there is a that here. Attends Oxbridge. All right. So which means that when we want to calculate for the attention representation or the attention score for boy, and boy is Q4. All right, Q4. It means that Q4 would be permanent in this case, but then what it would be calculating with is K1, K2, and K3. Don't forget, like I said, masked self-attention, which means that it is not seeing the words after it. It's only focusing on the words before it. Now, this is for training, all right? And then it does this. Now, what this happens is that it calculates the dot product, which is Q4 dot K1, all right, Q4 dot K2, all right, Q4 dot K3. Don't forget that we already explained that K3 in this case is what is what do I represent. So it looks for what is represents, what A represents, what Daniel represents, and finds the dot, tries to correlate what each of those words represent to what am I looking for. So boy, in this case, boy, what am I looking for? I always look for an answer. Oh, A, what do you represent? Is, what do you represent? Daniel, what do you represent? Okay, now this is how I'm able to first compute the dot product for this, for the word boy. And I've not used V. All right, I've not used V. So to not jump ahead of the gun, let's just keep them individually here. Let me see here. Okay, then separate them. So dot products like this and like this. Now, once it has computed for this would now be what you call weights. Weight to the actual value of the word boy. So this what will now come here would now be let's say A is equals to Q4 dot K1. All right. Basically, what will happen here will now be a cross product between A and V. Don't forget, in this case, V will be V4 because we are still trying to calculate the attention score for the word boy. I hope I've not gone so far. So once you calculate for each of the dot product between Q4 and K1, which is what you are looking for, and what I represent, we'll now bring all of them together and say we want to now do the cross product between the dot product of Q4, K1 and V4. V4 is basically what information do I contain? That's information that boy contains in itself, right? And then, of course, if B is equals to Q4 dot K2, right, it will now be this plus this. Now, this value, all right, is going to be the attention score for the word boy. Now, I'm still talking about LLMs as its simplest form. I mean, this is just one sentence. Imagine this being done for millions of sentences. Don't forget that LLMs are trained on large amount of data. Of course, they have to be tabulated, they have to be prepared well to now train the model on these sentences, of course. But this is how it works, right? So on one sentence, this is how it works. So the same information you've done here, you do it for A, you do it for Is, you do it for Daniel, you do it for that, you do it for Athens, you do it for Oxbridge. Now, there's something we call cursor mask. Now, remember I said it is masked attention, which means that when you're calculating for the attention score, you're not using the the values after that word. Those ones are masked, all right, during training. They are masked so that the neural network, right, is not aware of those words while it's trying to calculate how important it is or what information it should carry. Now, a simple diagram, it was until recently I actually learned that all the cursor masks, you hear about cursor masks, it's just very, very simple. All right. And yeah, so in doing that, I'll show us what cursor mask is. So in doing that, for example, let's use our Daniel. So Daniel is a boy. Now again, of course, Daniel is represented by Q1, is represented by Q2, A is represented by Q3, then boy is represented by Q4. All right, now it's like I'm drawing a matrix, right? So in this case, you have Daniel here, but this Daniel here is your K1, is your K2, A is your K3, boy is your K4. Now, what this means is that if I'm trying to calculate the attention score for Daniel, all I need is just K1. That's Q1 of Daniel, all right, and K1 of Daniel. Okay, now if I'm trying to predict for the word is, all right, I'm using the K2, all right, I'm the Q2 and K1 of Daniel. Then, of course, the Q2 and the K2 of is for itself, all right. So you still have to find how important it is for itself, all right. In which case, what is being done is that at this point, the other, of course, you cannot just leave these ones empty. As you are masking them, they have to be replaced with something. They cannot just be empty. Now, they are masked where you got negative infinity. All right. Now, of course, because we are using attention mechanism, it means that when you're saying Daniel is not supposed to have an idea of what A is. So the same thing here. Then what boy is, the same thing here. Now, the same thing too for A. Because A comes after Daniel, so it means we are going to have Q3 dot product of Q1. So of course it's needed. The value will be written here, of course. Q3 dot product of K2 is needed. Q3 dot product of K3 is needed. Then this goes to negative infinity. Now we come to boy. Q4 K1, Q4 K2, Q4 K3, Q4 K4. Now if you notice something, all right, if you can see my screen well, you notice that there's a pattern that has emerged where the negative infinities are, they decline, right, as you go down the sequence or the sentence. Now, the reason why we need this is that after we've computed for these values will be most likely very large. The dot product will be mostly large. Now, sorry, don't forget that during the case of all that watch the machine learning class, we talked about how that you have to normalize or standardize your data before you put into a neural network, because during computations like dot product or cross product, most values can be extremely large and will distort how the model or the neural network learns from the data itself. The same thing goes here, because we are doing the cross product between the value of this and the V. So which means that for V1, it will just be K1. No. So for the attention score to be K, let's do something like this. Q1 dot K1 times V1. Now imagine the value of Q1 dot K1 very large times V1. You actually have a very, very large value. Right, and imagine all these values are also in different places too. You have very large values, and it will distort the learning or the understanding of what each of these words represents. So which is why at this point you will now have to because these are logits, all right. So for us to now be able to reduce this, what we will now perform what we call a softmax. So a softmax activation function will find a way to reduce the values reduce this high value, all right, and then the softmax, when you apply a softmax activation function on negative infinity, what you get is 0. So essentially all this will be turned to 0, all right, when you apply the softmax activation function 0, which means that again, of course, since you can't leave it empty, you are masking them. Again, you cannot exactly add 0. So you want the computation to lead to 0 by itself naturally. So eventually, by the time you now have your final score here, it means that for Q to K2, you have something like A, let's say A21 plus A22 plus 0 plus 0 plus 0, because the other ones are masked. All right. Now, this is what goes beneath. This is how LLMs are trained, essentially. All right. Now, this is how you now compute attention scores. Now, of course, you get a score, and these scores are logits, all right, logic digits, and they don't exactly make sense. So that's why you have to perform softmax activation function on them, right, to now make them look like probabilities, all right, and then the values now begin to make sense. Okay, and this is why I say they look like probabilities is that for a case of, let's say, is, right, is, what I mean by A21 is because you are doing the dot product between Q2 and K1, then you are now crossing it with V1. All right, and you also do Q2 K2. All right, no, so this will be for V2 times V2, so A22. All right. So once you calculate once you use a softmax activation function to calculate the probabilities, use to calculate probabilities for this course, you just have in a straight line. Don't forget you're adding them, right? In a straight line, you just have the value of this A21, calculate as A21, A22, then 0, 0, 0, 0, showing the probabilities of each word in the sentence to its importance of the word is. So you show probability of this, probability of this, of course, probability of this to how important is in the sentence would be 0. So that's why you have to, convert them to probabilities to make sense. Now, these probabilities, of course, will now become the new vector representation of each of the word. Now, they are not just any vector representation. They are vector representations that now have meaning based on the other words in the sentence. Again, the idea of self-attention. At this point, we've actually done self-attention end to end. And then these representations are taken through, various linear conversions, normalization. All right, I don't want to go deep into that. All right, there's the add. They also there's a place where you do add. You also do normalization. There are places where, so there are different layers. So don't forget that there are different layers. Okay, so each layer tries to work on the representation and try to perform different linear normalization techniques on each of these representations. So you arrive at, let's say, final value. All right. So you arrive at what you call a final value. All right. Now, before I come to the final value here, I also have to now explain to us, because for some of us that will now go and read the attention is all you need paper, you will see something called multi-head attention. Again, one of the differences between your transformer architecture and your RNN is that you see during training, all right, these processes that I'm doing, they're all done in parallel. So what I mean is that the same way you are computing for, the attention score for Daniel, it is at the same time you are computing for the attention score of is a boy, that, like that. You are computing for them in parallel. So it's not as if you are computing for Daniel first, then go and do is, then do a. No. All right. So you are computing for them at the same time, because of course you are training. So you are doing it at the same time. All right. Now, the idea of multi-ed is, this is also where the magic happens too. You know how we've said that LLMs have what you call emergent abilities, which means that most times what they are trying to do during training is not exactly equivalent to what happens after training. So for example, there are certain abilities that LLMs can do. So you know how before we started having large vision models, we have models that can generate images, even if the initial iteration of these models were agentic in nature. All right, but we don't want to go into that. We don't want to go into how initial iteration of LVMs, right, or visual language models or VLMs were agentic in nature, which means that they were just a mix of language models and computer vision models, like oh, she just left my mind just now. Yeah, or let me just summarize that computer vision model. So they're just I want to generate an image of this, that. Summarizes, picks out the important, objects in that your sentence, pass it to a computer vision model that tries to put pieces together and bring back the answer for you. So that's why initially we had LVMs or VLMs that were just generating nonsense. All right, some tried, all right, but then again, what we are trying to do with large language models, there's limitations when we are now trying to correlate it to images and videos. But right now, we've seen advancements with video and the rest. So what I'm saying right now is that emergent abilities are things that they never thought that these LLMs could do. For example, now, normally, even before now, you say, oh, I want you to create a graph for me on a particular system architecture. You would see the LLM using strokes. How many of us have expressed that before? You see LLMs using strokes to generate an architecture for you, right? Like a tabular format for you. I'm like, oh wow. It was not as if it was trained to do that. Don't forget again, it is trained to predict sentence by sentence, right? Word by word, next token prediction. So how it was able to know that I need to predict space, one stroke, space, come down, space, two strokes, space, come down, space, three strokes, I was able to do that is what we call emergent abilities, which are abilities of large language models that were not modeled from were not modeled during training. Now, where that happens is what we call multi-head attention. Multi-head attention. Now, multi-head attention will take me back again to QKV, right? So I don't lose track. Now, here, take me back to QKV. Now, don't forget I said QKV are computed based on the word embedded or word vector representations of each of those words. Again, you can compute different QKVs you can compute different QKVs depending on the kind of computation you are doing. So which means that you can have what you call QA, KAVA, QB, KB, VB, QC, KC, VC, and these are what you call single head. What I explained earlier is not a single head. Then when they all come together, they'll be called multi-head, of course, single head. Now, each of these single heads have different use cases, all right, during training. For example, one of the heads might just be focusing on semantic representation. All right, semantic representation of each words. And that might be focused on phonetics. All right, how maybe each words are pronounced, stuff like that. And that word might be focused on should I say synonyms or just representations of that word in different grammatical and literary lights. So this is how your LLM is able to capture different representations of a word. And that's why we ask it, what is the synonym of cat? Okay, what's synonym of go? It means, move or something. Or when you ask it, I need, so that's a synonym. Or when you ask it something like, what is another pronunciation? Okay, what are words that sound like, in the words cat, you have mat, you have sat, you have pat, all right? Because I was able to capture these representations or these meanings in different heads. This heads is what I explained earlier, the QKV process, which means that there's a QKV meaning for all the words in your sentence, which means, like I said, QAQV. So you have something like if you have Daniel, so still using our Daniel is a boy, All right. I would say Daniel is K1, Is is K2, A is K3, Boy is K4. It means that we would have what you are. We would have something called QA1, QB1, QC1. All right. KA1, then VA1. This is just for Daniel. So imagine you have like 20 multi-heads. It means that you compute for all the multi-heads in parallel. It's just the same again. You are computing for the attention score for each of the words too in parallel. So all these things are happening at the same time. So you are computing for QA1, KA1, VA1. All right. You're also computing for QA2, KA2, VA2. You're also computing for QB1 at the same time. All right. And this is the beauty behind, or the beauty of transformer architecture. That way you can be able to capture so many meanings, so many semantics, so many representation of every word in a sentence. And that's how we have our ChatGPT looking beautiful as it has always been. All right. Well, that was sarcasm though, but that's how we have our models very good. They look like something. I mean, they look like the next best thing after sliced bread. And that was a leap that we're able to get from models like LSTMs and RNNs, which did not capture this kind of representations, these kinds of semantics, this kind of meaning. So when you hear multi-head masked self-attention, I'm sure we can boldly say what it means. All right. Multi-head, which means that you have different meanings or different semantics captured individually on each of the words in a sentence. Self-attention, because every word in that sentence contributes to each other to give what you call an attention score, or what you call a meaning, right? Proper meaning, attention meaning, right? And then masked, because the representations after a particular word does not contribute to the attention score of that word, so that it doesn't capture in, so that it's able to learn without expo, all right, without having an idea of what the resulting values should be. Now, this is what you have when you are training a large language model. And this is what goes on, this is what goes beneath your LLM architecture. All right. Moving forward, for the sake of time, now we understand what multi-head attention is. All right. Now, the question is, okay, if they are being trained this way, what do I mean, how do we know, how does the model know it is learning well? All right. Now, I stopped initially at you get a final value here. All right. Now, this value, so yeah, so this value, of course, too, is a representation of whatever processes as each of the words have undergone in your neural network, depending on how you design or architect your neural network. Now, every model has what you call a word dictionary. Claude has its word dictionary. One. Open, okay, let's say, should we say Claude now? Okay, let's put it as model. Let's not take it to, let's say Sonnet as it is. GPT o3 has its word dictionary 2. Now, what is a word dictionary? Now, a word dictionary is a compendium of every word that has been exposed to that LLM, which means that Sonnets might have 50,000 words. GPT o3 can have 100,000 words that it is exposed to, that it knows. So, which is why when you hear things like LLMs cannot give what they don't have, it's true. It can't just generate any meaningful word out of vacuum. All right, because each of these words have, like we've said, token IDs. And these token IDs, of course, have what you call vector embeddings. So LLMs are garbage in, garbage out. To even be more precise, they just overfit on the data that you fed to them. That's why they are this good. All right, so that is why the current iteration or the current development of large language models are not close to what we want to call um, um, the a general model. All right, they are not close to what we want to call that super model. Okay, so they are not close to AGI. Yes, so that's what I'm looking for. Yes, thank you very much. They're not close to AGI because of how they are being modeled, how they are being architected, and how they are being trained. All right, so every model has its word dictionary. So which means that by the time we've computed again, by the time we've computed for the final representation for is, which means that we want to now predict the next word called A. Don't forget that as you are training, you have your full sentence. So which means that A already has its own token ID. Don't forget. Now, once it has generated its own representation. Now, this representation gotten from these processes are used to compute what we call logits again, right? Logical digits for every word in the dictionary. What I mean by this is, once it has got to the final value, all right, vector rep for is, that vector rep is going to be part of the processes used to compute what you call logical digit or logits for every word in the dictionary, and to compute it. All right, after also computing, those are just normal words, they don't mean anything. For them to mean something, you also have to know what you compute. You now have to compute what you call probabilities using your softmax activation function to compute probabilities like we did after we're able to calculate the dot product between Q and K. All right, so softmax to compute probabilities, which means if you are saying Daniel is A, we have a probability of 1 because that is the actual answer. Now, what I mean by A, I mean this A would have this A is 1. All right, A is 1. Now, it's very much possible that, of course, there is A within the dictionary. So A here can be 0.3. So Daniel is a boy. Daniel is going can be 0.2. That's probability of going being the answer. Church can be 0.01. Mosque can be let's say 0.225. Now, it computes these probabilities for all the 50,000 words. Now, we can apply what we call greedy decoding. What greedy decoding just does is you pick the probability, pick the token with the highest probability, which is 0.3. All right, so let's not use A. Let's assume A was 2, going was 3. So the highest probability here is going. So which means that it now gets going. So the model has now predicted that going is the next word after is. Daniel is going. Meanwhile, in that sentence, A is my next word. So what is now done at this point is since if it gets A is 1, all right, since it did not get A, right, it just calculates the difference between, right, A, value of A, which is 1 here, and the value of A, which is 1 here, and the value of going here, which is 0.3. All right, and then it calculates the difference, and that's how it's used to now. It now does back propagation. All right, the idea of back propagation, it has found the difference again. At this point, it just calculates the loss function. Loss function is just the difference between what is predicted and what is the actual value. All right, and at this point, it uses that, right, based on the loss function to now do what you call back propagation. And that is now adjusting, the weight of your neural network backwards to be able to now get deep, to be able to now adjust for the error gotten from your loss function. Now, this is how LLMs are trained and adjusted. So it's not as if he gets it during training exactly. So he knows that, oh, what I'm missing is by 0.7. It means I did not convincingly predict each word. So it means that with the error of 0.7, I need to adjust my weights backward. So I need to use back propagation to adjust my weights like that, going back. So again, those of us that listen to the neural network class, you understand what back propagation is. But that's how you can be able to adjust for your error. And it does this for every single sentence. Now, do you know the interesting about this is that by the time he's doing this, it's going to get to a point where at least it gets that optimum value for ease. All right. Now, the trick with this is, when you say ChatGPT, I have Daniel is a boy. I want you to give it to me in another language or in another word. You know what is happening there? Is that, again, those of us that have used those of us that are using APIs, right? LLMs APIs like your GPT API, your Claude API, you can tweak for your temperature. I know that the higher the temperature, the more creative it is, the lower the temperature, the more specific and direct it is, right? What is going there is that each of the value has logits, right? As like each of the words actually has the probabilities now that have been converted from logits. It just switches. So in this case, if you say you want to increase your temperature to 0.5 or 0.7 or 0.8, it means that instead of doing greedy decoding, that's picking the highest probability value, it just picks the top 5. And that comes from your top K2. So top K2 is another parameter in your model configuration that chooses what top probability values do you want your model to be considering every single time. So if you say top 5, it means that if you ask your AI to switch a particular word, right, 7 times or 10 times, it will only give you those words between those 5 top probabilities. So when we think, this LLM is able to, I said it creatively gave me this word from this one sentence. I told you that this sentence I have, I want to give it to me in another way, right? Give it to me in this way. I'm like, oh wow, how did you do it? It's not magic. It's just playing with probability. So I see large language models as algorithms standing on probabilities. So in this case, going might be 0.3. A might be 0.2. Church might be 0.7. If you say top K equals 3, what is doing at that point? At that point is just switching the words based on the probability. If you use the first one, it use the second one. Where's the third one? All right. So that's what happens. So it's not as if there's one magical thing. It's just switching the words based on their probabilities. So when you have stuff like top K equals 5, it means for every word you are generating, consider the top 5 probability. Of course, there's also top P and there's temperature. All right, so I'll talk about this. If I have time, I'll talk about this at the end of the class. All right, but now with the top K, we know that it's considered the top 5 probabilities. But again, you can decide how you want to. During training, you can decide how you want to choose the answer in your 50,000 words. You can use greedy decoding, which is the word with the highest probability. But there are some times where the word with the highest probability is not the answer. All right, so that's why it's called greedy, because it's greedy, but it doesn't always work every time. So there are also other processes that you can do to pick the optimal value for your answer, because that's the value you'll be computing the loss function for. All right, now, so this is what is done during training. And I want to show us something. I want to talk about inference. Now, that is doing training. Don't forget that it does that for every word, right? So that's once it computes for is, and maybe it got going, and actually what is in the sentence is A, it knows that it needs to adjust. But once it does this for all the words, and once it gets it for all the words, it now computes the average loss function, then takes it backwards. So it's not as if it computes loss function for each word. Of course, that's not computationally sensible. So it does this, it calculates loss function for every word, That's because it does it in parallel. For every word, find the average and then now take it backwards. So it don't, and this is why the average makes sense, is because every word still contributes to other words in the sentence. They now have what you call attentive relationship, right? Attentive relationship. So that's why the average would make sense in this sense. Now, that's during training. During inference, you know how when you ask ChatGPT, what is the value of, oh, don't let me spy on something interesting. Who is the king of England? And it goes ahead to think. Again, let us not forget that when we ask ChatGPT, we are also adding tokens. So just like the way when when you're using a model API, right? You have your tokens, your system prompts, even ChatGPT, OpenAI has your system prompt too. All right. So means you are combining your system prompts, or they are combining their system prompts with your question. Now, what happens here at inference is that yes, is that because we are doing next token prediction, you only have to focus on the last word. In this case, you are focusing on, so let me take away the question mark, because question mark is a token itself. You are focusing on the word England. And you know why? Again, it's because you are predicting the next word. It's because who will also contribute to what England stands for. Is will contribute to what England stands for. D will contribute to what England stands for. Of will contribute to what England stands for, including the system prompts that have been added to your questions. Each of those words would contribute to the last token, which is England. All right. It's now based off this that the next word would now be answered. Oh, now there's a reason why it is going to use the word D. Sorry about that. Okay. Um, okay. All right. So now this is why it will start from, oh, the king of England, is because this D itself can be said to be, we can call it beginning of sentence, BOS, which is a defined token that OpenAI would have chosen to say, oh, once you are trying to answer any question, maybe when you see something like this, a question mark or something like that, this is going to be the default token for you to start with. So the LLM does not struggle with how it's going to start generating words. So it's to now start with D. Then, of course, now keep computing. Now, like I'm trying to explain, it still competes for the attention score of England, all right, based on the other words before it. So now talk about, oh, the king of England is, King Charles, or the king of England is King Daniel, or the king of England is, King David. All right. Now that is what happens during inference. It does not need competing for the attention score of king, of D, of who, because already those Q and V are computed already for England already. So there is no need. All right. And then as it keeps generating words, it keeps computing for the attention score of this. Each words. Again, don't forget that each word will now be added to, of course, this. So when it's saying the king of England is King Charles. Sorry about that. King Charles. All right. It is using every token before it to even arrive at the word Charles. Now, so that's the magic that actually happens when you once you prompt ChatGPT. It still does the attention scoring, but uses both your question and the system prompt for context to be able to generate your answer for you. Again, it does it one token at a time. Now, this one is very fast. All right, is because it runs on thousands of GPUs. Now we understand why compute power is needed for training, and not just training, inference. So which is why they said sometimes is there's no need to be very polite to LLMs, saying thank you, because it's just adding more information that is not needed to the actual generation. Now, based on what I've just explained now you now understand why the better you prompt your ChatGPT, the best results you get. Like I explained, every word before the answer it gives to you, every word in your question, every word in the system prompt. Let's assume OpenAI system prompt is perfect. Now, every word in your own question has to be relevant and has to be perfect, so that once it's computing for the attention score of each of those words, it makes meaning and it cannot give you the best answer. But try it. Try typing. Try like typing or asking ChatGPT a question, and don't complete each of the words. So, like let's say you want to put who is the president of Nigeria, you put WH, then I, then PRE, you put NIG. I mean, it doesn't make sense, right? Or maybe you are faltering in spelling. You find out that the AI will not even be direct with the response it's giving to you because it doesn't still understand what you need. So that's why they tell you there's a reason why there is something called prompt engineering as a course, because some people till now do not still understand how to prompt AI models. So it's just wasting a lot of compute power and compute time, because you have to keep going and going and going, just arrive at a particular answer. But be able to structure your needs and be direct with it to the AI to give you the perfect answer. Now, with this knowledge, you now understand that if there's a mistake in the system prompt of OpenAI, no matter the question you ask, you'll be getting wrong results. I mean, if there's a very, very significant mistake, right, in OpenAI system prompts, you keep getting terrible answers, because those system prompts are part of the attention scoring processes to derive your answer. Now, this is how you do LLM from training and LLM to inference. All right. Okay, I still have a bit of time. Don't know if I've covered almost everything. Okay, yeah. Lest I forget. I remember the process I've been taking us through is a masked self-attention. But there's also something called self-attention. All right. There's a use for self-attention that is not masked. So let's call it unmasked self-attention. Which means if you are saying Daniel is a good teacher, and you want to try and predict, or doing training, you want to predict for the word A. It means that good will contribute to the word A, teacher will contribute to the word A, at same thing, is will contribute to the word A, then Daniel will contribute to the word A. Now, why is this important? Imagine you are trying to do stuff like sentiment analysis. So the use of self-attention processes is seen in models like BART models. All right. Now, this is why this is important. Yes, we are doing stuff like self sentiment analysis, where you have a sentence like, "I am a good boy." All right, a good boy. Now you want to understand the sentiment of this sentence, whether it is positive or negative, which means that you can't just use the previous words to get the sentiments of this sentence. You need every single word to understand what sentiment this sentence carries. Now we see why you cannot do masked, because every single word has to contribute to each word in the sentence to now give that sentiment of whether it is positive or whether it is negative sentiment. All right. Even stuff like processes like uh classification. Yes, you want to classify something, you want to classify a phrase as anything. All right. not classify a phrase as anything. You need every single word in that phrase or in that sentence to contribute to what, to contribute to what the phrase stands for, or to what class each phrase belongs to. Now, this is where the idea of unmasked self-attention, which is full self-attention mechanism. In other words, they call this encoder only, why the masked self-attention is called decoder only. So masked is called decoder only. Decoder only transformer. Why full self-attention is called encoder only. That's unmasked, by the way. Now, there's a meeting point where you have both encoder and decoder. All right. And you see this in I think you see this in models like T5 models. Can't remember. You see this in T5 or T4 models. Now, what this does is that the processes that is done in the unmasked self-attention, all right, which is let's call it self-attention or full. So let me use the word full. So full self-attention is added to the processes you do in the masked self-attention, both of them together. So it means that just the way just the way you do the generating of the eventual vector representations, you're unmasked. You do the same thing for masked, but you're not covering the future tokens. You are leaving it open. Now, once you've generated for each vector representation, you now pass it again. Don't forget that the input into your masked self-attention is a vector representation. So it means that when you're not getting the vector representation that is the result of your encoder-only architecture, it is now passed as input into your decoder-only, which is your masked self-attention. Now, use cases where this really is important is translation, right? Translation tasks, all right? Mostly when you're trying to do language translations, all right, where you understand that you have to first of all understand the meaning of the sentence before even generating it one token at a time. So if I'm trying to say Daniel has gone to the market, so the market, this is English. Daniel ti lọ sí ọjà, all right, this is Yoruba. You know that it is not just about predicting the next word, because the way languages are designed, the meaning of that language, of that sentence, can be at the end. In fact, a noun in English at the end of the sentence might be at the beginning of another language. So just doing actual translation word for word would not make any sense. So you have to first of all understand the meaning of the sentence using full attention. Then you now add that to predicting next word attention. That's next word masked attention. That's word for word in the other language. So that at least the AI can also be able to understand semantics between each word in that language and generate it words one at a time. Now this is where we have both the encoder and the decoder only architecture. All right, so now we see the different use cases between the encoder only, as seen in full attention, like classification, sentiment analysis use cases, or even summarization, to our decoder only architectures that powers most of our large language models right now, like your GPT, Claude, name them, Gemini. They are all decoder only architectures, and they use masked attention, all right, to both encoder and decoder architecture, where we use them in language translations. So these are the differences between the subfamilies of the transformer architecture, or in other words, your LLM architecture. All right, so I think I think I'm done with everything. Well, as we go on in classes, you also, I think right now, I'm sure that we can, if I'm to call somebody now, you have an idea, even if it's not as deep, right? But at least you understand how LLMs generate words. You just work on probabilities, right? So next time you're in front of your Claude model or you're in front of your ChatGPT model and you're asking it a question, you already know in the back of your mind that, well, said, if I ask this question now, it's generated the attention score already for the last token based on the previous tokens, including the system prompt. All right, then start generating it one token at a time while it keeps generating the attention scores for each token till it ends the sentence. Right. Now, there's a question that usually comes. Oh, how does the LLM knows it's supposed to end the sentence? There are different techniques. All right. There is end of sentence token, EOS. Yes. End of sentence token. That's when as the LLM keeps generating words, it keeps generating words using attention score and probabilities. It will get to a point where the probabilities don't make sense. That's when it keeps generating words, it gets to a point where it doesn't make sense. At that point, he immediately just ends it there with an you know, end of token or end of sentence token. Now, this is designed from, I think, the middle layer of the entire LLM framework. That's their entire LLM and SOC engineering, right? So that the LLM is looking out for. Or again, there's also they also have special tokens that the LLM looks out for. So once that's generated that special token, it knows that this is where it needs to end. All right. So there are stuff like that. That's how it knows that it needs to end generation. Once that hits a special token that has been designed from the beginning. Okay, once you see this token, know that once you've generated, once this token has ended up being the highest probability in your word dictionary, know that you need to end generation. All right. And then you have stuff like that. And there's also word counts. So there's also, okay, don't generate more than 20 tokens in your responses. So it knows when it's generating, it needs to end that. So it counts, needs to end at this token. So there are different ways in which LLMs know when to end the sentence, right? Don't forget, there were times where it would just end suddenly, right? It just stop middle of generation. Okay, so that because it has hit its token limits. And there's also token limits. It ends at, there's a token limit. That's what I mean, the total number of tokens it should generate. So at that point, the LLM did not gracefully, wrap up its generation. So there are stuff like that. There are also techniques where if the LLM start repeating, if it repeats, so once it's generating word for word, I know words now turn to sentences. Once it starts generating the same sentence that looks like the previous one, all right, there will be an action for it to stop generation. That means there's no other meaning it's getting from the previous words to give an answer to that question. Then it stops. So it also has to look out for duplicity in generation. So there are different ways that these hyperscalers in LLMs, as these big organizations like Gemini, Claude, and like Google, Anthropic, Meta, OpenAI, mention their names. They do for each of these models to make them better. All right, and I think with the understanding of this, once you go down into papers like multi-agent frameworks, I also want to advise us to study mixture of experts, the mixture of experts paper. All right, you'll now see how these LLMs look very good. You will understand what goes beneath your GPT-5. At least you have an idea of how GPT-5 works. Right now there's nothing new that is being created, so it's just engineering. Now there's a glass ceiling on science right now. All right, what we have is just engineering, right? Combining different things to solve a problem, and these things already exist. So I don't know, I'll try and see if I can send you the paper for mixture of experts, and for those of us that might not have the attention is all you need the paper. So that at least you have an idea of, with this foundation on attention is all you need, you would understand how the mixture of experts work, right? Or the foundational agentic AI works. So yeah, with that, I don't know if anyone has a question for me. I just have like three more minutes to the end of the class. Yeah, does anyone have a question? I'll be happy to answer.
Hello. So can you please just refresh again
Any
the
question?
yeah, please can you please refresh again the idea of self-attention,
I'm really
please?
sorry. Let me unmute myself. I think somebody was speaking. Yeah, sorry, please, can you, if you're asking a question, please, can you start again?
Yes. I was asking, could you please refresh just the concept again of self-attention? Please just refresh it. I just want a holistic grasp of it.
Okay. So the idea of self-attention is that every single word in a sentence contributes to the prediction of the next word token. Now, every word is a token, or every word can be converted to a token, which is the numerical representation of that word. Now, every token is mapped to an embedding, which is the vector representation, all right, in a high dimensional space of that word. Now, in the prediction of the next word, that's the next token, LLMs or the transform architecture works with next word prediction, right? In the prediction of the next word, it's not just dependent on the word before it, it's dependent on other words before it to capture, the semantic meaning in that sentence. All right. Now, once it does that, and that's what you call self-attention. All right. It captures the semantic meaning, or it captures contextual, let me use the word contextual meaning of the previous words to what is being predicted. So that it's not just predicting a word randomly based on just mere mathematical calculations. It has also captured linguistic representations of the previous words to actually now know what to predict better. All right. Now, in a transformer-based model, right, self-attention it can be masked. MASKED. Now, the idea with masked is to corroborate the idea of next token prediction, which means that if other words after what needs to be predicted for is seen, right, during training for that particular word, the LLM does not exactly learn sufficient, it does not learn sufficient it does not now become self-sufficient when it learns representation. What do I mean by that? If for example, as a young man, I live my life every day making decisions, and from each decision I'm learning. But if I'm able to know what is happening tomorrow, what is happening next tomorrow, what is happening on Tuesday, all right, and I'm making decision, I already know what decision needs to be made. So again, because of that knowledge, I would not form naturally as a human, because I won't be able to make those mistakes that I need to learn by, because those mistakes are what will shape me. Now that is what also that just summarizes the masked attention, right? It's a masked self-attention, because the LLM needs to be able to learn by mistakes, be able to predict the word without having a knowledge of what the word is. Now that's why it needs to be masked. So that's why the future of being uncertain is a blessing, because it forms us, it even improves our cognitive processes. Now we know what decisions to make we know what thought processes to have in making a decision. Now the same thing, so the model needs to know what representations to have to even be able to predict the next word, instead of just doing the next word outrightly. Now that is what your self-attention does in the simplest form. I don't know if I've been able to capture something for you. Okay.
Right. Thank you.
Yeah, you're welcome. Any other question? Oh, you want to go into farming too?
So is there a book you can give us or something that can enable us to just grasp these concepts? Because it's, to be honest, they're very involved and it requires deep thinking.
Okay, book. All right, I will look out for one. Okay, first of all, I will share the two research papers I spoke about, or maybe I'll share just one. All right, so I'll share the one on attention is all you need. All right, and then I'll look out for a simple material that would talk about this. I think there's one that comes to head now. I think it's mastery, ML mastery, machine learning mastery. I'll try and look for it, and it might not be a book, it'll just be a URL, right, to a material, and then I don't know if that works, if that's okay.
Thank you.
All right. Thank you very much, Mr. Akin. Right. Yes, you want to go into farming too. All right. uh well, I it is well. I'm still considering it, by the way. But then don't be shocked if I don't eventually go into farming. All right. The money might just keep me in the AI. Any other question? Any other question? Okay, so could I share my journey, like how I got here, cause it's some complex stuff. All right, so okay, starting it this way briefly, right? So I know that they will start ringing me now to end the call. So let me see what I can share in 5 minutes. First of all, is that I'm a science student, right? And knowledge of mathematics, knowledge of statistics, having that foundation was a big lever for me, right? And then my sojourn into AI was not just because I wanted to study AI. In fact, I had been doing AI before ChatGPT. So I had most of the, right now there are issues with knowledge. Most of the knowledge that people need to have, foundational knowledge. There's a lot of people are skipping it, right? Students of AI are skipping it because you don't need to know how neural networks work. You don't need to know how LLMs work before you build an LLM application. All right. So anybody can just sit down with a 6 hours course on how to, work with LLM models or APIs and how to do prompt engineering and say he's an AI engineer. But I had been doing machine learning and AI before 2023. And I got into that field because of my love for robotics. And then, of course, robotics is hardware, which means that you need money. You need to be spending money regularly to buy components. And if there's anything that needs to happen to the components, you have to start afresh. And as a student, that kind of fund was not readily available. So I had to switch to the software side of things, which was AI, because I've always wanted to build AI optimized robotics, especially in the field of computer vision. And so I was like, okay, why don't I wait till when use the Elon Musk style, right? He was a fan of hardware, but you need software brings the money. So build the software, like you build PayPal. So I had to now switch to software, then started learning data science. So I was a student of data science for a considerable long time and machine learning, even before I started doing computer vision and neural network. So I already understood how models work from foundational principles, right? How algorithms work, how these models use this data. I had that foundation, right? Then boom, came ChatGPT, right? And I was like, okay, it was just translation of existing knowledge. And then it's just extension of what needed to be learned, what I needed to improve on. And so what I've been speaking on right now is not in knowledge of 6 months, 7 months. This is combination of about 4 years. All right. 3 years. Let's say 4 years, right? And there have been a lot of downsides too. Like, okay, there's this new thing. I need to learn it. Now there was once upon a time, data science was not really the hot thing. So I was in that era where data science was not like the hot thing. But then AI came and it looked like, well, um, law of serendipity, Lady Luck favors he who is prepared. And so when AI started, when no now again, not when AI started, when we now had commercial access to LLMs like ChatGPT and the others, right? I didn't have to learn so much. I just needed to understand this new technology. So it was just an upskill in my existing knowledge. So everything is still connected, whether it is ML, which is still under data science, whether it is neural networks, all right, that's deep learning, everything is still connected. They still have the same foundational principles. You have model, understanding data, and splitting out resulting computation. As simple as that. So it's not been easy, even till now, as I work as an ML and AI engineer, it's still not easy, right? Because you have to keep up with new things, new techniques, All right. And so, yeah, that's just, I've used
Mr.
5 minutes.
Daniel,
Yeah. So,
so
yeah.
sorry to just, can I butt in here quickly? Why is it that Geoffrey, people like Geoffrey Winton and so on, they're scared of AI? The way you break it down, you make it so like easy in terms. I'm not so much easy as you make it very the knowledge accessible, and you really have a granular, seemingly a granular understanding of what AI is capable of in terms of it's not being dangerous. Let's say it that way. But other people who are in it are terrified. They said these things can lead us into a lot of problems. Can you give us an idea of it?
Okay. Admin, please permit me to answer this question, if I may. All right. So, as an engineer, I understand this AI at this I understand AI at granular level, which means I understand the limitations of AI. But we cannot still take away the fact that on the application layer, um, there are still challenges. Now, there's no new technology that never had these challenges. Even during the dot-com boom, there were still challenges with web applications. And that's where we now started having even during the emailing, during when email was like the real thing. We started having issues with that's when the era of Yahoo started coming about. People doing phishing, right? People doing those other fraud-based frauds, those other types of fraud that came around with emailing, right? Email frauds and other things. So every single technology has its bane. So as long as it's man-made, there are always downsides. All right. It's how we are able to manage it over time. So it's not, if you look at it right now, even the idea of email is not so perfect. That's why we have spam emails, because of the issue with people sending you, phishing sites, and you click from
Yeah,
your email. People are still
I
struggling
understand
with
that.
emails.
You're going to abuse of process there. What I'm talking about is it technology itself? Is it dangerous? Is it inherently dangerous to man? As in, can the stuff become self-aware or whatever? Geoffrey Winton was. Other people are saying that can now become
Oh,
like Terminator.
self-awareness.
Yeah, Terminator.
Oh,
All of us have seen Terminator. We're all terrified that it's become like Terminator for everybody. Is
kindness,
it?
you mean? All right, we are very far away from a Skynet issue. Very, very far. You see the way I broke down AI, you know that there are limitations to it. The idea of the idea of AI being sentient, I think we are very far from that kind of technology with what we have right now. All right. So any scare for AI being sentient, AI being, the next, the realism form of Skynet, we are far from it. All right. It's just that, again, knowledge. All right. People are different. How we analyze problems are different. As an engineer, analyze problem differently from the way someone who doesn't have technical knowledge of these things will analyze it. All right. Somebody will see AI generating a love note and see, wow, AI is generating a love note. Wow. It's going to affect relationships, or people no longer be. I mean, what come on, right? Yes, that. I mean, it's still application eventually. I mean, okay, look, for example, nuclear power, the idea of nuclear power is the cleanest form of energy, but there are the downsides to nuclear power. The same thing with AI. There would be advanced use cases of AI that would even help make human processes more efficient, but there's a downside. But if it's for the sentient thing, I think we are actually very far from it. With what we are doing right now, we are very far. Will it get there? Uh, maybe not. But if there's anything I know about humans, we are very resilient. So, well, what is his name now? Meta's AI chief will say, for us to achieve AGI, um, it doesn't believe that the current transformer architecture can help us achieve AGI. Trying to remember his name. I don't know. I mean, I'm forgetting their names these days. Who can help me remember Meta's AI chief? Ian LeCun, yes. Ian LeCun believes currently that the transformer architecture can lead us to AGI. So we'd have to come up with something better than transformer architecture to even achieve sentient AI. Yeah. So yeah. So right now, I think we just have to focus on the positives while we try to reduce the negatives. Mhm. All right. So any other question? Any other question? I think in the absence of none, if you do have one, please drop it on the group, and I'll try and squeeze out time to respond to it. But yeah, so that's it from me. Thank you, everyone. Thank you very much. Yeah, good night. Good night, everybody.